All right, there we go. Sorry, I just came from a Twitter Spaces, so I'm a little bit frazzled. But welcome to Reading Group. I really had to stop and think about what I was welcoming you to. Howdy, y'all. We are going to be reading a paper. It's been a while since we've done this. And this particular paper is about a specific machine learning pattern, I guess. Oh, one sec. My noise canceling is off. Hold, please. All right, that should fix it. Sorry about that. So this particular pattern, Grokking, is pretty similar to double descent. We're going to talk about all of this in a second, but I just want to show you what it looks like. So zoom, 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 zoom. For those of you who are familiar with validation and training test trainings and validation set accuracy, goodness. The sort of general thing that you're looking for is over time, accuracy should improve, but they should improve to, oh my God, sorry. I'm trying to describe overfitting and I am a sleepy baby. Okay. As you train your model and it gets a better, ability to represent the underlying patterns in your data, it should get better and better. At some point, it will have gained a good sort of general understanding of your data, and then it will start to overfit. So it will begin to describe the specific patterns in your data set that may not, generalize to the world. And the longer you train it, the more you are overfitting to the data, the more parameters you have, the more data you have, et cetera, et cetera. And what this paper found was that if you keep training well past this step, they got a point, so right around here, yeah, you can see my mouse, so well after you'd seen overfitting, which is when the red and the green line separate, basically, the green line went up to the red. And what that means is, suddenly at some point during optimization, the model basically perfectly understood the problem and was doing great. So that's the green line and the red line meeting. That is surprising. That's not generally how people understand machine learning to work, especially in a statistical model where there is over and underfitting. So underfitting is not having enough explanatory power for the data that you have, and then overfitting is having explanatory power for your specific variables, but not necessarily for the population as a whole, and this is not that. So this is pretty similar to double descent, which we'll talk about in a little bit, but kind of surprising, right? Not the pattern you generally see or expect to see given a statistical framework. Which is to say, let's read the paper, and then I'll talk a little bit more about why I chose to look at this. But before we do that, I think it would be helpful to show that this same pattern has been reproduced. Nope, it's been replicated. So replication is when you take pretty much the exact same study and try to get the exact same results. So in machine learning, that would be holding as much of your pipeline and your data parallel or as close as possible to the original paper. And this result has been replicated by a couple people, actually. So this is on GitHub. This is C-Snell, SEA-SNELL. And as you can see, same pattern. We have the overfitting here in the middle, and then after a lot of optimization steps, suddenly the validation pops up, and you get really, really good performance. And then Teddy Coker, that's Teddykoker, also on GitHub, again found the same sort of replication. So you have the training, which is this top blue line here, goes up, it diverges from the validation line, and then after many optimization steps, your model basically solves the problem, as it were. And then third person, this is Tom Lieberman, I think, and just sort of the same pattern. So this top line here is, this top graph here is the top line in all of those other charts, and this bottom graph is the bottom line in the other charts. And as you can see, as we go through the steps, the training accuracy goes up really high, and then the validation accuracy lags for a long time and then goes up. And I do want to point out, just for you, and as we read the paper, I think this will all make sense, but these bottom numbers here, the steps, are all in the thousands. So this happened around 2.5 thousand optimization steps. This happened at, what's that? That's probably 10 to the 4.5-ish. So, thousands of optimization steps. And then this one was also happening around between 10K and 100K. And these scales are all logarithmic except for this one. This one is linear, all of the rest are logarithmic. So the increase from here to here is 10 times the increase from here to here. So that's the pattern. With all of that in mind, it's a pattern, the authors found it, it's since been replicated in, holding things steady, pretty much the same problem. Let's read it. So the paper is called Grokking, Generalization Beyond Overfitting on Small Algorithmic Datasets, and we'll talk about what those are. It was presented at almost exactly a year ago, because ICLR acceptances just went out for 2022. The first Mathematical Reasoning and General Artificial Intelligence workshop at ICLR 2021, and that's the International Conference on Learning Representations. It's a machine learning conference. Also, the chat is being extremely quiet today. Hope y'all are doing okay. And it is by Alethea Power, Yuri Burda, Harri Edwards, Igor Babuschkin, and Vedant Misra. And my apologies if I said anybody's name wrong, and they are all from OpenAI. Abstract. In this paper, we propose to study generalization of neural networks on small algorithmically generated datasets. In the settings, questions about data efficiency, memorization, generalization, and speed of learning can be studied in great detail. So basically what they're saying is we are making datasets. That's what algorithmically generated means. So how much data do you need to answer a specific problem? Is your model just memorizing the data, right? Is it really overfitting? Is it generalizing? Will it be able to handle new instances of this thing? And how fast is it learning? We can study these really well because we know everything about the data because we made it. In some situations, we show that neural networks learn through a process of grokking, in quotes, a pattern in the data, improving generalization performance from random chance level to perfect generalization, and that this improvement generalization happens well past the point of overfitting. So the point of overfitting would be around 100 here, where these lines start to diverge, for your reference. Christoph says, we are listening. Okay, good. I always worry that maybe the audio's cut out and nobody can hear anything. Just a note on the word grokking, it's from a science fiction novel. I would say that it's something you hear a lot of people who have been in technology for a while use in an informal context. It means to understand, basically. So it's not I guess it's a technical term now, but it's a nerd word, I would say. I say that as a nerd. We also studied generalization as a function of dataset size and find that smaller datasets require increasing amounts of optimization for generalization. We argue that these datasets provide a fertile ground for studying a poorly understood aspect of deep learning. There's many of them. Generalization of overparameterized neural networks beyond memorization of the finite training dataset. So they're saying that when they had a very small data set, if they just optimized long enough, suddenly the model would seem to understand. All right, and I believe these are arithmetic data sets. I haven't read the paper yet, but I believe so. So you could teach a model arithmetic, but the smaller your data is, the more rounds it takes to happen. And also, they mention here in some situations. So this is something that we'll talk about. I don't think there's good consensus about situations where this occurs, except that we know that it does occur in these situations with a particular type of algorithmically generated data set. So TBD. Elias, definition of grok, transitive verb, to understand profoundly and intuitively. Thank you. I believe it's from Starship Troopers, the novel, which I would not recommend reading, personally. Can't say as it has my stamp of approval. All right, So generalization of overparameterized neural networks beyond memorization of the finite training data set. So basically, overparameters means, very generally, that you have more parameters, so trainable weights, usually in the case of deep learning, in your model than you need strictly to represent your specific data points, right? So a model is overparameterized in relation to a specific data set. And what they're saying is, okay, so we have these big data sets, lots and lots of connections. So transformers, great example of something that has a lot of connections. And it looks like they're not just memorizing the data, they're able to generalize to other situations. And there definitely is some degree of memorization that happens, particularly with something like a transformer language model, but also there is some degree of generalization. So they're proposing that this would be something that might help to explain that phenomena. Introduction. The generalization of overparameterized neural networks has long been a source of interest to the machine learning community since it defies intuitions derived from classical learning theory, more like statistical models, that sort of thing. In this paper, we show that training networks on small, algorithmically generated datasets can reliably exhibit unusual generalization patterns, clearly decoupled from the performance on the training set in a significantly more pronounced way than such effects manifest on datasets derived from natural data. See Figure 1 on the left, for example. So this is an example of the grokking. I was like, I don't think that's an example of the usual pattern we see. Such experiments can be quickly reproduced on a single GPU, and this makes them convenient test beds for theories of generalization. In the datasets, we consider our binary operations of the form A, B equals C, where A, B, and C are discrete symbols with no internal structure, and is a binary operation. Examples of binary operations include addition, composition of permutations, and bivariate polynomials. So they're generating math problems, basically. Training a neural network on a proper subset of all possible equations then amounts to filling in the blanks on the binary operations table, much like solving a Sudoku puzzle. An example is shown on the right in Figure 1. Since we use distinct abstract symbols from all distinct elements A, B, C involved in the equations, the network is not made aware of any internal structure of the elements and has to learn about their properties only from their interactions with other elements. For example, the network doesn't see numbers in decimal notation or permutations in line notation. Okay, so you know that A were involved and B were involved and what the output is, but you don't know what A is, I think is what they're saying here. Let's pause and go back to the figure. So this is the grokking that I talked about. Let's zoom way on in. And the general expectation based on, like they mentioned, classical learning theory is that the training would go up and stay up, and the validation would go up for a little bit and then diverge here around 10 to the second, so like maybe 105-ish optimization steps, and then diverge, and that would be the point of overfitting. Also, I never said what these lines represent, so this is validation on, so this is looking at the output of the model given the same data it was trained on. So data it's seen during the training process, that's the red line on top. And then the green line on bottom, I realize that these are not very discernible if you have red-green color blindness. The green line on the bottom is on held out data. So this is data the model has never seen. This is data it's already seen. And the idea is that if you're doing really well on data you have seen and very poorly on data you haven't seen, then your model is overfit and it's just describing the patterns in your training data and not generalizing. And what they're saying is you keep going. Eventually, your model does generalize. Evo Lawsy, sorry if I'm saying that wrong, says, are we learning AI? Yeah, I'd say so. We are reading a paper about a specific phenomenon that happens sometimes during training and what situations where it occurs. All right. So that's the grokking phenomena, which I showed you all really quickly has been replicated. And this is Steps Until Generalization for Product and Abstract Group S5. So this is showing how long it took, and this is how much of the training data they used. So this would be almost all the training data. This would be very little of the training data. The blue circles represent runs that reached greater than 99% validation accuracy in 5 times 10 to the 5th updates. So these are the models that grokked. And the red ones are runs that didn't reach 99% validation accuracy in 5 times 10 to the 5 updates. And then this is the update where they did reach it. So the more data you got, the faster this grokking happens. And if you have too little data, it doesn't matter how many steps you do, you're not going to find this phenomena. And I would say that the specific thing that they're trying to model here, right, these binary operations are pretty straightforward. Certainly in the realm of natural language, this type of very, very simple operation is extremely rare. All right. So I think this is an example of the star operation. So A star A is A, B star B is D, A star B is C, B star B is D, C star B is D. So it's learning this specific matrix, and the training goal is to fill in these questions in this matrix. And just staring at this for 2 seconds, I have no idea what those would be, but it's some sort of binary operation. Okay. We've looked at the figure. Let's hop in to their contributions. Also, this is a pretty short paper. ICLR papers often are. So it's just 4 pages and then references and then appendices. So I feel like we'll get through it. I know we're 20 minutes in. All right. Our contributions are as follows. We show that neural networks are capable of generalizing to the empty slots in a variety of binary operation tables. We show that long after severely overfitting, validation accuracy sometimes suddenly begins to increase from trance levels towards perfect generalization. We call this phenomenon grokking. An example is shown in figure 1. We present the data efficiency curves for a variety of binary operations, so like how much data do you need to solve the problem? Navan says, what kind of optimizations are we talking about that bumped up the validation accuracy? Oh, so that's just rounds of optimization. Like training epochs, basically. I'm guessing is what it's. I would be shocked if it wasn't epochs, but I haven't finished the paper, so we'll find out. But basically, the longer you train, time, I guess. We present the data efficiency curves for a variety of binary operations. We show empirically that the amount of optimization required for generalization quickly increases as data size decreases. We compare various optimization details to measure their impact on data efficiency. So to your question, Naveen, it depends on the details, and they will discuss it in more detail. Detail. We find that weight decay is particularly effective at improving generalization on the tasks we study. Okay. I'm not entirely sure what they mean by weight decay. I mean, maybe the weights are regressing towards a norm. We visualize the symbol embeddings learned by these networks and find that they sometimes uncover recognizable structures of the mathematical objects represented by the symbols. So basically what they're saying is, hey, we show that a phenomena occurs. This sort of grokking phenomenon, which as I mentioned is similar to double descent that we'll talk about in just a sec. I think they also talk about it. The data efficiency curves for a variety of binary operations. I don't do a lot of binary operations day to day, so I'm not going to be as interested in that. We show the amount of optimization required for generalization quickly increases as data set decreases. So the suggestion is if your data set the underlying pattern is capable of showing this grokking behavior, and I don't think we know what types of underlying patterns those are, then if you get more data, you don't need to optimize as much, which is great. And then looking at the details, and then some model analysis looking at the outputs. Elias says, look at figure 2 for the optimization, not operation. I keep trying to say operalize. I got this. I've got it. No, that can't be operational. Anyway, I can't say this word. That's okay. We're just gonna keep moving on. Method. All of our experiments use a small transformer trained on data sets, equations of the form A, B equals C, where each of A, B, and C equals and C is a separate token. Details of the operation studied and architecture, training hyperparameters, and tokenization can be found in Appendix A1. All right, experiments. Generalization beyond overfitting. Deep learning practitioners are used to seeing small improvements in validation accuracy after validation loss stops decreasing. A double descent of validation loss has been documented in some circumstances, but it is considered unusual among practitioners. So double descent. I have a slide prepared. So this figure is from the paper Another Step Towards Demystifying Deep Neural Networks by Michael Elad, Dror, Simon, Avid Aberdam, and Avid Aberdam. I'm sorry if I'm saying y'all's names wrong. It is not my intention. I just don't know how to say them. From the Proceedings of the National Academy of Sciences. And the basic idea is I mentioned, so this is flipped from the other thing that we've been looking at, right? So this is the Grokking terms that we've been talking about, and if you just flip it twice, basically you will get this particular type of model. So this is the same iterations over time, and this is the amount of error rather than the amount of accuracy. And the general thing is, as you keep training, your training error, so this is the error on the data that you've already seen, goes down and down and down and down over time, which is what you would expect. Your error on your held out test data set that your data hasn't seen goes down and down and down, and then it goes up, and then it goes down again. So the sort of general way that this is, I don't want to say just so storied, but the general idea for why this happens is that as your model learns, it begins to sort of pick up on the broad strokes patterns that are represented by your data. And then it starts to really overfit to the data itself. And eventually when you have, enough parameters trained for long enough, it stops overfitting and then goes back to generalizing. And sometimes people will talk about it as this part is the classical learning, statistical modeling overfitting, and then this is the sort of underlying deep learning that's slowly beginning to learn these patterns and eventually takes the test error down. That's kind of the general way that people describe it. And again, it's not super consistent. I don't think that we have, as a field, a good idea just looking at a data set of whether or not this is going to happen given a specific data set and a specific model architecture. So that's what double descent is. Similar. On the small algorithmic data sets that we study, improved generalization after initial overfitting occurs for a range of models, optimizers, and data set sizes, and in some cases, these effects are extremely pronounced. A Kentucky table? I don't know if that's what that is. Sorry if I'm wrong. It says relations are binary operations with binary results. Helpful. A typical example is shown for modular division in figure 1. This one that we talked about. There we see that validation accuracy starts increasing beyond chance levels only after 1,000 times more optimization steps than are required for the training accuracy to get close to optimal. In figure 4, the training validation losses are also plotted, and we see double descent of validation loss. Where's figure 4? That's figure 2. Where's figure 4? That's figure 3. Is this figure 4? Yeah, there we go. Okay, so this is the double descent of validation loss. Right, so down is better, and it goes up. So it tracks with the training data, and then they diverge, and then eventually, after a lot of optimization steps, it reconverges with the training data. Back up to where we were. Figure 4. We found these behaviors to be typical for all the binary operations for dataset sizes that were close to the minimal dataset size for which the network generalized within the allotted optimization budget. For larger dataset sizes, the training and validation curves tended to track each other more closely. So this seems to happen when you have a small amount of data and a lot of time to train, I guess, would be the point there. Section 3.1.1, learning time curves. I'm going to take a drink of water. In a typical supervised learning problem, decreasing the amount of training data decreases the converged generalization performance of the model when the optimization procedure is capable of interpolating the training data. So what they're saying is usually if you have less data, your model's less good. In our setting, we observe a different phenomena. While the converged performance stays constant at 100% within a range of training data sizes, the optimization time required to achieve that performance grows quickly as the data set is decreased. Okay, so they're saying if you have less data, you can still get as good of a result, but the more data you have, the faster it happens, which is a slightly different pattern, I guess. Pattern makes sense. Figure 1 center shows the median number of optimization steps until validation performance first reaches 99% for the product in the abstract group S5. In the vicinity of 25 to 30% of the data, a decrease of 1% of training data leads to an increase of 40 to 50% in median time to generalization. So if you have 25 to 30% of the data in this specific I would say that these percentages are not going to hold for any arbitrary data set. This is for specifically the data set that they're using, that a 1% decrease in the amount of training data led to a 40 for 50% increase in training time to get this Grokking effect. Well, the number of steps until validation accuracy is greater than 99% grows quickly as the data size decreases. The number of steps until the training accuracy first reaches 99% generally trends down as dataset size decreases and stays in the range of 10 to the third to 10 to the fourth optimization steps. We've observed a similar pattern of exponential increase in optimization time until reaching generalization as data size decreases on all the algorithmic tasks for which, pardon me, for which we could get the networks to generalize. I couldn't mute in time. My apologies. Okay, and I'm guessing the specific tasks are going to be mentioned in the appendix, so they weren't even able to get the models to generalize in all situations for their specific subset of tasks. All right, grokking on a variety of problems. We've measured the mean accuracy across 3 runs for training data sets consisting of different fractions of all available equations for a variety of binary options listed in Appendix A 1.1. The results are presented in Figure 2. So this data set is finite, and they know the percent that they have of it, right? So this is, that's the data set. There are only so many squares in the middle of this. Punnett square is what my mind is saying, but this is not a genetics problem. There's only so many squares in the middle of this chart, graph, chessboard. You know what I mean. Sorry, it's been a fairly long day, and I'm having trouble languaging good. The processes, the underlying processes which generate language are theoretically at least not finite. So I cannot, you can't say, hey, here's a human language. You have X% of this human language represented in terms of data. So that's just a side note for language specifically. Where was I? 3.1. Here we go. Since the operands presented to the neural network are presented to the neural network as unrelated abstract symbols, the operation x plus 1, mod p minus 1, and x times y, mod p, with a prime number p and non-zero x and y are indistinguishable from the neural network's perspective, And similarly, blah, 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 blah. Basically, this is because every non-zero residual modulo of prime can be represented as the power of a primitive, blah, blah, blah. Anyway, they're saying this is a hard thing to learn, and I don't think we care about the details. I don't. Y'all can go back and reread the paper if you do. Some of the operands are symmetric, and some are not. Symmetric means it's reflected over the center. So if it were symmetrical, which it is not, this would be D, and this would be D, this would be A, and this would be A, this would be E, and this would be E. So like error matrix, or covariance matrix is symmetrical. And they're just saying you need less data because there's an underlying pattern. Such operations tend to require less data for generalizations than closely related non-symmetrical counterparts. We believe that this effect may be partially architecture dependent, since it's easy for a transformer to learn a symmetric function of the operands by ignoring positional embedding. Navin says it's more like nagging than grokking, poor network, because you keep asking well after the training fitting is quite good. Some operands, for example, x to the third power plus x times y to the second power plus y mod 97, didn't lead to generalization within the allowed optimization budget at any percentage of data up to 95%. The converged models effectively just memorized the training data set without finding any real patterns in the data. So these just straight up overfitted and were also underfitted. It sounds like both. It sounds like they both did not understand the underlying pattern and also memorized the data. To such a model, the data is effectively random, so it's not able to represent the underlying process. The operation x divided by y mod p if y is odd, otherwise x minus y mod p, requires the network to learn a mix of several operations. In particular, the role of x has to be interpreted as a residue in the additive group when it's paired with an even y, and as a residual in the multiplicative group when it's paired with an odd y. This shows that generalizations can happen even for operations that are not cleanly interpretable via group or ring operations. That's some number theory that I don't care to dig into. So they're basically saying, hey, our models can do some things and not some other things, and question mark, which problems can it do, which problems can it not? I don't think they have a strong theoretical explanation for that, but that's also just sort of what machine learning research is like these days. We tried various forms of regularization to see what can induce networks to generalize better on our datasets. Here we present the data efficiency curves on a particular dataset S5 for a variety of interventions, and they're using this dataset as the example throughout the paper. Full batch gradient descent, stochastic gradient descent, large or small learning rates, residual dropout, weight decay, and gradient noise. The results are shown in figure 2. So they just tried a bunch of different stuff. Figure 2 is above us, right? We already looked at that. Yeah. So this is that, and I know this is all quite small, but this is looking at different tricks, and this is looking at different operations. Left, different operationalization is the thing I was trying to say earlier, but that's not this word. Different optimization algorithms led to different amounts of generalization within an optimization budget of 10 to the 5 steps for the problem of learning the product in the abstract group S5. Weight decay improves generalization the most, but some generalizations happen even with full batch optimizers and models without weight or activation noise at high percentages of training data. Suboptimal choice hyperparameters severely limit generalization. Oh no. Not shown, training accuracy reaches 100% after 10 to the third to 10 to the fourth updates for all optimization models. So basically what they're saying is doing different things really affects how much this shows up. And sometimes if you choose the wrong things, it just straight out doesn't. So this first one, full batch atom, it looks like towards the end here it's bouncing. So 0% validation accuracy, then 100, then 0, then 100, then a 0, then 100. That feels like it's probably stuck in some sort of saddle in the space. So like if the decision region has a saddle shape and you're sort of bouncing back and forth across it, That would be what my guess is there. And some of them go up really fast. So atom optimization with weight decay 1 did pretty good. And then there's a bunch of, interactions there. Right. Best validation accuracy achieved after 10 to the 5 steps on a variety of algorithmic datasets averaged over 3 seeds. Generalization happens at higher percentage for data intuitively more complicated and less symmetrical operations. What? Sorry, that last sentence made no sense. Generalization, so this grokking thing where the ability to, no, that's not just grokking, that's just like, did you learn the pattern? Does your model work? Happens at higher percentages of data, so you need more of the available training data for intuitively more complicated and less symmetrical operations. So the harder something is to do, the more data you need based on your intuitions of how hard it is. Okay, I think that's fine. That also is, I think, how most people think about machine learning problems. So here's this one in the bottom that is just flat. Oh, I can zoom in. I've got the power. So this is the one that they said they just never generalized. They did not get it. And the point that they're trying to make is the easier it is to learn the operation, the less data you need. So this one, pretty straightforward. This one, pretty straightforward. This one, where there's like an if statement in the middle of it, you need more data for this validation accuracy to happen, is the point that they're trying to make there. So it depends on, let's zoom in on these. So it depends on your hyperparameters, and it depends on how complex your problem is. And that's what they found. And I would say that all of these operations are less complex to model than pretty much any linguistic operation. I don't know, there's probably some sort of language problems that are in this range of complexity, but I don't know that you'd build a neural network for it. You'd probably just use rules. Anyway, this is the discussion of the types of problems, which we read, the ablations, and then the qualitative visualization of embeddings. In order to gain some insight into networks that generalize, we visualized the matrix of the output layer for the case of modular addition and S5, this particular data set. In figure 3, we show a t-SNE plot of the row vectors. This is just embedding space visualization. For some networks, we find clear reflections of the structure of the underlying mathematical objects in the plot. For example, the circular topology of modular addition is shown with a number line formed by adding 8 to each element. This structure is more apparent in networks that were optimized with weight decay. Cool. Cool. I think not super relevant to me, but I sure do see some patterns. And I imagine these lines here are added post hoc. All right. So basically what they're arguing with this is that, hey, our models are, able to capture something about this underlying structure. We have seen that in data sets we studied, small algorithmic binary operation tables, effects such as, that's the type of data sets they studied, effects such as double descent or late generalization, and improvements to generalization from interventions like weight decay can be striking. So I think they would probably argue that this is a special case of double descent, which is a known phenomena. When does it happen? Question mark. In this case, it does. This suggests that these datasets could be a good place to investigate aspects of generalization. For example, we plan to test whether various proposed measures of minima flatness correlate with generalization in our setting. So that would be the minima in the, error topography, I guess. I don't know. Wow. Speaking of language problems, I'm having a hard time saying words. So if you have you're stuck in a minima that's like very flat and you don't have a slope to go down for your gradient descent, like there isn't a gradient, does that change things? TBD. We've also seen that visualizing the embedding spaces of these neural networks can show natural kinds of structure. For example, in problems of modular arithmetic, the topology of the embeddings tends to be circles or cylinders. We also see that the network tends to idiosyncratically organize embeddings by various residues. While the properties of these mathematical objects are familiar to us, but not to me. I don't know that I've ever had a class in number theory. We speculate that visualizations could one day be a useful way to gain intuitions about novel mathematical objects. Okay, this is all math stuff, I don't care. That's rude. I'm sure that they care quite a bit, but it's not relevant to me. In addition, we document an interesting phenomena where the number of optimization steps needed to reach a given level of performance increases quickly as we reduce the size of the training data set. Since this represents a way trade compute. Since this represents a way to trade compute for performance on smaller amounts of data, it would be useful to investigate in future work whether the effect is also present for other data sets. And then references. So that's the paper. So it's a specific phenomena that they're finding that is, I would say, a pretty extreme example of double descent. And I think it looks a little bit more extreme because of the fact that this is, logarithmic, but even on, linear increases, it's still a pretty dramatic change. And as I mentioned, it's been replicated. So using the same type of problems, multiple people have gotten the same sorts of results with this particular data set, with this particular type of problem, and using a transformer structure. Yes, it looks like you can get this striking behavior where your model is super overfit, and then pretty quickly that overfitting is overcome and the model begins to generalize really, really well. So up here where the training and validation accuracy are basically the same, that would be evidence in the fact that the model can generalize because it is explaining variation in data it hasn't seen just as well as in data it has seen, which is the ideal, right? That's what you want. A conducting table says the lines show the result of adding 8 to each element. So that's in this one. Oh, so plus 8, 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 plus 8. Got it. Thank you. That's helpful. So some thoughts on this. So there's been replication again, so that's on the same data set with the same problem, and that's what all these links are to replications. But I don't know about reproduction. So being able to consistently find the same training pattern on other types of data set. And I have some tweets that I've pulled up here. So this is somebody, Pajiter Thiel, I'm guessing that is a joke name. I don't think that's this person's real name. Tried to replicate on SVHN data. So that's a computer vision set, I believe, of numerals, and was unable to find the same effect. And then Alethea Power, you may recognize them. They are the first author on the paper, said in response to somebody saying, I'll just read the whole thread. So they said, a couple of people have reproduced on small algorithmic data sets, but I don't know of anyone who has tried it on a larger naturally occurring data set yet. So Pajiter did, no luck. Jules replies, why not? Isn't this an obvious reaction to want to test it on a natural data set? And then Alethea replied, yes, but doing so could take a lot of compute for a long time with no guarantee of payoff. And I think that's, for me, the main takeaway of this paper, because I've been seeing a lot of discussion about it recently. I've just been seeing a lot of discussion of double descent. And the type of algorithmically generated problems here, right, are just fundamentally easier than modeling human language. And I don't mean that to like dunk on mathematicians or anything. It's just easier to have a formal representation of, numeric operations than it is of language operations. Anyone who's ever done a lot of work in like formal semantics can attest to that. Even within a formal framework, it takes a lot of work to capture meanings in a formal way, and it is not straightforward or easy. And if it was, people would already have done it. Language would be solved. It's interesting. There's sort of this eternal optimism, particularly in computer science, that, solving language is just right around the corner, and it never is. So that's the author's take on how extensible this is, right? Can you reproduce these same sort of effects on natural data? And the answer is maybe, but they were on this very small data set, on this very small transformer. They're finding the effect at, 10,000 plus optimization steps, right? Like a lot of optimization steps. And if you have a very large model, especially a lot of language models tend to be quite large. I'm sure some of y'all are familiar, have used them in the past. That's a lot of training time for, again, no guarantee of result, right? We don't have a good formal classification of the types of underlying problems where this will happen and where it won't. And even within the world of like specific binary options where you have all the data, right? Like you can generate 100% of the possible outcomes of a specific optimization or a specific binary you can generate all the data, right? You can create the population, which is, again, just not a thing in language because of the generative nature of human language. The amount of compute you would need is something, very something. So this is my sort of 2 cents. I think it's an interesting paper. I'm always happy to see more focus on, smaller models. And I think that in particular, data efficiency is really important in the natural language setting. And those of you who are building Rasa chatbots, and especially if you're, providing your own data labeling, can definitely appreciate that having to label less data is important and saves you time. But I wouldn't chase this, right? If you're working in language, I wouldn't try to see if you can get this effect. So first of all, we don't know what type of problems it happens on within specific compute constraints. It could happen on all of them if you train for, a theoretically infinite amount of time, but we just don't have, any guarantees of that, which is just true of machine learning in general, right? We're in the guess and test stage. Also, the amount of optimization steps is significant. So again, these are, I'm just going to pull up their main figures. So this is in Make Big. There we go. So this is, logarithmic. So this is what, 2.5 orders of magnitude more training steps, which is, so at this point is probably where I would stop training, right? If I just been sort of like checking in with the model as it was baking. And at this point is where I would stop. So this is like what, 100 rounds of optimization. And they're finding, this full optimization at, 1 million? Is that 1 million? 10 to the 6 is 1 million, right? 1 million rounds rather than 100. So that is a lot of time and a lot of money. And also thinking about the potential environmental impact. I don't know, that's something I care about. I hope it's something you care about. That is a lot of compute and that's a lot of electricity. So I think my general advice, Rachel, you wrote this ahead of time. Yes, I think it's also true of double descent, is if you have extreme data paucity, right? If you have so little data, maybe you might get a benefit of increasing training time dramatically, but you're going to get more benefit if you increase the amount of data. So since you have a limited amount of time and resources, that's probably what I personally would focus on. And if you are working on a very simple problem, like if you're trying to create a deep learning model to do arithmetic, maybe don't do that. Maybe use a calculator and use that instead. That I think would probably make your life easier and give you faster results for the same output. So, Aki table or Kentucky table. Again, I'm sorry, I don't know your name. If we learn how/why it happens in small cases, we might be able to predict when it might happen in large ones. Otherwise, it's uneconomical in NLP. Yeah, absolutely. And if there's a ICLR is coming up, so if we got good theoretical guarantees about specific data distributions where we can count on this, then yeah, absolutely, the field's changing. I'd love to be able to tell you, the secret trick to getting the perfect model. But as far as I know, it doesn't exist. So. Yeah, and I think that this person is probably a spammer, so I'm just gonna remove that message. Apologies if you are a real person. Try not to paste weird looking links. All right, so that's the paper. There are a lot of appendices, so if you care about math a lot, you can check them out. That might be relevant for you. It's available for free online, and the link is in the description of the video. Next week, TBD, we'll do something, and I believe our office hours are going to be with Paul, I want to say. Let me double check. I want to make sure I'm not telling y'all wrong things, because you won't get so excited for office hours with somebody, and it'll be somebody else great, but you'll be sad. You won't get the person you were looking for. Yes. So I'm going to be back for office hours with Paul, who is fantastic. I think we're going to have a great conversation. Come bring your questions. That's going to be Wednesday at 9 a.m. Pacific, which I think is 11:30 p.m. IST. I could be wrong about that. Apologies if that's incorrect. And then next Friday, we'll do something else, TBD. I've got a couple things that I've been thinking about, so I'll do something for that. So hopefully this was helpful and informative, and you learned a little bit of something about machine learning. I think this is really cool that it happens sometimes. I think it's, increases our understanding of deep learning. I call it probably like a special case of double descent, maybe. Yeah. All right, thanks for joining. We'll see you on Wednesday for office hours. Have a great weekend. Stay safe, stay healthy, and I'll talk to you soon.